Hi everyone, I'm Mattia. I'm going to present my work guiding pseudo-labels with uncertainty estimation for source-free unsupervised domain adaptation that we will present next week at the CVPR 23 main conference. In this work, we present an approach for source-free unsupervised domain adaptation. Under this setting, a model is trained to adapt the knowledge learned on a source domain to a target domain, without the use of target labels and source images. Our approach produces noisy pseudo-labels by inferring on the target data using the source model. The source model is then progressively adapted to the target domain by refining these pseudo-labels. Our method aggregates the knowledge from neighbor samples to refine the pseudo-labels and estimate their reliability to guide the model with more accurate pseudo-labels. To improve the refining process, we propose a novel negative pair exclusion strategy that adapts standard contrastive learning approaches to work with noisy pseudo-labels. During the pseudo-labels refining, we could encounter scenarios of low uncertainty where the neighbor samples share the same class and scenarios of high uncertainty where the neighbor samples belong to different classes. Following this observation, we propose to compute the entropy or the average of the neighbor's prediction to estimate the uncertainty of the refined pseudo-labels. Low entropy values correspond to low uncertainty, while high entropy values indicate high uncertainty. Finally, by using the exponential function to entropy values, we obtain the weights for the classification loss. For improving the refining process, we employ a contrastive learning framework. Standard contrastive learning methods do not use class labels. Others look only at the current pseudo-labels to create the set of negative pairs. These solutions are not optimal in presence of noisy pseudo-labels. We thus propose a novel negative pairs exclusion strategy based on a temporary queue that stores prediction of the last epochs. Our solution excludes those pairs composed of samples that share the same pseudo-labels at least once in the last t epochs. Using this strategy, we reduce the amount of pairs that are incorrectly included in the negative pair list. Our final loss is composed by three different losses. The first is the classification loss. We use a negative learning loss in order to handle the noise in the pseudo-labels. The W in the equation represents the pseudo-label's estimated uncertainty. The second loss is the contrastive loss, in which we use our negative pairs exclusion strategy. The third loss is the divergence loss in order to avoid the posterior collapse. Results shown in this table show that our method outperforms state-of-the-art methods by a large margin. Finally, this plot shows that our method is able to refine the pseudo-labels by handling and reducing the noise contained in the pseudo-labels. This enables our model to be trained with more accurate pseudo-labels and to be better adapted to the target domain. This link contains the paper, the project page and the code. We invite you to join us at the CVPR 23 poster session of Tuesday afternoon, number 336, for more details on our work. Thanks for watching.